Okay, where did we leave off? So here's what we know. We know that commercial software being used to predict recidivism is not particularly accurate, 65% accurate, and seems to have a racial bias issue, number one. Number two is that when we polled people on the internet on Mechanical Turk to do a similar task, they had the same accuracy as the commercial AI software, and they seem to have the same racial bias, despite the fact that they don't have information about race. So whether they knew race or not, they had that same bias in terms of the errors they were being making. So that leads us to two questions. How is it that both the software and the humans, not knowing race, are not race blind? That's weird, and we should understand that. And perhaps more importantly, how is it that AI being used in the courts is as accurate and as biased as random people on the internet? These aren't even judges, lawyers, social workers, and people in the criminal justice system. These are people being paid a few bucks on the internet. And we need to get to the bottom of both of these, and that's what we're going to do in this segment now. All right, so here's if you will, a toy picture of how an AI algorithm might work. So you have a little box here that I'm gonna show you what that looks like computation a little bit. That's your AI, that's your decision making. And you feed it some information. In our case, the information we fed to our human reviewers were sex, age, the crime they're accused of, the crime degree, misdemeanor or felony, prior crimes, juvenile felony priors, and juvenile misdemeanor priors. So these were the 7 pieces of information. We feed that information into, well, for humans, into the brain, and then we make a risk assessment. And now what we're going to do is we're going to feed that information into an AI algorithm, a classifier, if you will, that then has to make a prediction. Okay, so let's think a little bit about what that box might look like. Because if we're going to understand the race blind problem and the accuracy problem, we've got to start to get at what is happening in these AI algorithms. Okay, so let's unpack that box a little bit. All right, now to keep things simple, let's imagine I only have 2 pieces of information, and you're going to see in a minute why I do that, because it makes visualizing this box a little bit easier. So imagine all you have at your access, and I could have picked any 2. It's random. Is how old somebody is and their total number of juvenile felonies. That's all the information you have, and your AI algorithm now has to make a risk assessment. Okay? So one way to think about this AI algorithm is to think about these 2 pieces of data as in terms of the Euclidean plane. The age of somebody from 0 to whatever, and the number of juvenile felony convictions just up on the vertical axis. So we're going to train this algorithm. So what does that mean? We get a bunch of data where like the Broward County data that we use in our studies, and every point here is an individual. So this point corresponds to somebody that was this age and had very few juvenile felonies. This data point corresponds to somebody who was younger and had more juvenile felonies, and so on and so forth. So every point in this 2-dimensional space here corresponds to somebody that that was arrested. We have the historical data. We followed them for 2 years, and they did recidivate somewhere in that 2-year period. Good, training data. Now, we have another body of training data of people who didn't recidivate. And again, every data point here, I've just color-coded them differently because these are people who did not recidivate, right? So they were arrested, followed them for 2 years, clean record after that, okay? And that's their data. Now, that's training data. So what is the goal of an AI algorithm is now, given that you've seen these patterns, can you make predictions of people you've not seen? In the same way, when I started this lecture, I said, we may predict products you may like. We may predict music that you may like. We may predict whether we can give you a loan. How? You look at historical data, you look at the patterns that emerge, and you learn what is the likelihood of somebody not recidivating or somebody recidivating. Okay? And there's lots of different ways of doing this AI, machine learning. I'm going to talk about one very, very simple technique. And here's the basic idea. It's called a linear classifier, which in this 2-dimensional space, again, arbitrary axis, age and juvenile felonies, you draw a line. This is why it's called a linear classifier, because there's a linear separation between these clouds of data, the red data points and the yellow data point. Now, obviously, in a 7-dimensional space, I can still do this, but my separator is not a line, it's a hyperplane. So in 3D, it would be a plane. In 4D and beyond, it's a hyperplane. That's why I'm doing it in 2D, because I can draw this as a line. So the AI's goal is to learn this line that separates one class from another, people who did recidivate from people who didn't recidivate. Okay? So let's just talk about what that's going to look like. So let's say this is the classifier I learned, this line. Now I get a new person, that little blue dot right there, and they're on the left side of the line, which I've shaded red. They are predicted to recidivate, right? That's the nature of recidivism. By the way, you can see the errors. See that yellow dot right there and the yellow dot right there? That's a mistake. That's predicting somebody would recidivate when they didn't. And these red dots down here are the mistake. The classifiers are not perfect, but the majority of the yellow dots are there and the majority of the red dots up here. And once I learn that separating surface, I can put any data point into the space right there, and then I make a prediction. Which side of the line are you on? So if you're on the left side, I predict that you will recidivate. And if you are on the bottom line, like that blue point right there, then I say you are not going to recidivate. I have a classifier. Okay? Again, not perfect, but the majority of the yellow dots are there and the majority of the red dots are there. So how do you learn that line? Lots of different ways to do it. I'm going to just describe, just to give you some intuition on how this works, one classifier called a linear discriminant analysis. It's also referred to as a Fisher linear discriminant as well. So an LDA is the classifier I'm going to describe just very briefly. All right, here's our training data. This is so-called supervised learning. I have training data and I know the labels. I know that's a red, I know that's a yellow dot, and now my job is to learn a separating line, higher dimensions, it's a hyperplane, that will separate it. And how do I do that? I need some objective function. So here's the objective function. I'm gonna change this line from this separating surface to a projection. So now what I'm going to do is I'm going to find a line such that when I project all the data onto that one-dimensional subspace, I'm going to accomplish two things. The first thing is I'm going to minimize the within-class variance. So class is red, did recidivate, or yellow, did not recidivate. And what I want is I want to find a line that as I rotate through this space, all of the red dots are bundled up really, really tightly, and all of the yellow dots are bundled up really tightly. That's the within class, red, yellow, variance. So I want to minimize those variances so that everybody's tightly bundled up together. And at the same time, I want to maximize the across-class variance. That is, I want these red dots to be really tightly coupled and to be very far away from the yellow dots that are themselves very tightly coupled. Why? Why am I doing this? Well, if I can drive these dots apart from each other and keep them coupled, well, then I can separate them. I can draw a line down the middle and say red dots, yellow dots, one class, the other class. So this is the objective function for LDA. Different types of machine learning algorithms have different objective functions. Not necessarily good or bad, but this is probably the simplest one. You will learn this in your machine learning class almost certainly in the first week. It's really like the standard technique you always start with, and then you go from there. Okay, turns out, by the way, when you specify the problem as minimizing within class and maximizing across class variance, you can solve it using a generalized eigenvector problem. And I only mention that because you should take a linear algebra class. Just because you're a computer scientist, do not shy away from the mathematics. In order to do almost anything really interesting in the space of AI, machine learning, pattern recognition, image processing, computer vision, computer graphics, robotics, natural language processing, the long list of really cool things out there, you need to know a lot of math. So linear algebra, probability, multivariate calculus are really, really good things to spend some time on. So this LDA reduces to a generalized eigenvector problem that can be solved with one line of Python or MATLAB code. Really nice, really simple, very efficient. Now, once I have that classifier, I've learned this projection. I'm going to project all the data onto it. And now I have a classifier, but I need to make a decision. Where's my boundary? Right? So if everything projects onto this line right here, where do I draw the separation that I'm going to predict all these are red and all these are white, and yellow rather, and I have a choice. I can draw the line anywhere I want. So let's say I drew the line here. This will lead to a low false positive and a low true positive. What do I mean by that? So a false positive says that I take a yellow dot and I predict you as recidivating, right? I falsely accuse somebody of being high risk. But if I draw the line way up here, very few yellow dots are going to be on this side of the boundary, right? There's just that one right there. So I minimize the false positive. But also notice that a lot of red dots are down here, so I've also minimized the true positive. And that is when somebody's high risk, very few of them are being classified as high risk. So I can trade off the errors that I'm comfortable with. Now I can move the line. So if I move it down a little bit, I've got a slightly higher true positive rate. You can see more of the red dots are on this side. But I've got another yellow dot got caught, right? And as I slide down, what's going to happen? Well, eventually, I'm going to get to this point where I have a really high true positive rate. Most of the red dots are now being predicted as high risk, but I have a really high false positive rate. Look at all the yellow dots that have now gotten caught in the web. So I get to draw that line in the way that I want to balance these. Which mistakes do I want to minimize? What is the accuracy that I want? And I get to make that decision. Okay? All right. So that is, in some ways, the simplest possible AI that you can have for making this type of prediction. Okay? LDA, linear discriminant analysis. So now what I'm going to describe to you in the last segment of this talk is what happens when you have these 7 things here, and then what can we learn in terms of the commercial software, its bias, and why human performance is biased when they don't have race, and why are they as good as a commercial software. So once we're going to build a classifier based on some information over here, and then we're going to see if we can get insights into those questions in this last segment. So we'll be back in a few minutes to finish up.